In this video, I'll be taking a look at some of the ideas in our sampling and confidence intervals chapter, and I'm pulling some of the slide content directly from that workbook chapter. But here's what I'd like to take a look at specifically. The learning objectives will include the following. Why do sampling? Why not just work with population data? Then we'll spend a little bit of time taking a look at how to create random samples from population data, as well as some strategies for sampling methods. We'll also take a look at sample size calculations using sample size formula as well as sample size calculators. So, so why sample? Typically in the world of process improvement, we sample to better understand what's going on in the underlying population. We're trying to infer what's happening with the population or infer a population parameter from the sample that we collect and the calculations that we perform on the sample. It would be great if we always had access to population data and we could analyze and work off of population data, but sometimes that's impossible for a number of reasons. It might be too costly to go out and capture all of that data. Could be too time consuming given the time frame that we've got for this process improvement project. The in some cases, the population data that you might have access to is it's no longer a true representation of current state. I might have access to the 10,000 records in the database, but that contains examples or occurrences or transactions that occurred years ago, and since that time, the process has changed. Sometimes it's just impossible because the past is the past and we didn't do a thorough job of data collection in the past. And this crude drawing, I think, tries to describe it, where we take our current state sample. We hope that that current state sample will be a reflection of what the current state population is. We'll then analyze that data to determine root cause. Then we'll build solutions in future state. And in future state, we'll capture a sample again, analyze it, and hope that that information reflects what the overall population values will be. So there's the reason why we use samples. Now let's take a look at how to go out and capture those samples next. So how do we go about capturing samples? Let's assume in this first example that we actually do have access to population data and we want to grab a smaller sample to work from. When we do this, we're going to be doing what I call probability-based sampling. Let me turn on my pen here, probability-based sampling. And one of the first questions that I often get from participants or Lean Six Sigma Greenbelt project team members is how do I get a random sample? And one of the easiest ways, if you've got access to population data, is to use the random number generator. I've got two ways described in the workbook, but the simplest technique is to grab a database of values. So like in this example right here, I've got a whole bunch of items. Then use the random number generator to create another column of values right next to your actual items that you want to sample from. And then sort on the random numbers. That in essence shuffles the deck, and then grab the first 30, the first 100, the first 10%, the first 30% of data points that you've now got from your shuffled deck. Two ways described in the workbook. My favorite though is just the re-sorting based on random numbers. So now we've got a random sample. Now that we know how to create a random sample, we should also take a look at different sampling methods, the techniques or strategies that we go about in capturing our sample data. Let's take a look at some examples next. All right, let's next take a look at a couple of sampling methods that are common. We just got done taking a look at how to create what is called a simple random sample using the random number generator in Excel. Let me turn on my pen to circle that. Systematic sampling is an even simpler technique in which you basically grab every X version of a data point every 5th or every 12th or every 23rd. Stratified sampling is used when you know that the underlying population is broken down into large swaths or percentages, like 50% are of a particular ethnicity, and 20% are of another ethnicity, and 10% are of another ethnicity. So then you grab a random amount inside each percentage group, so stratified sampling. And then cluster sampling is done when you know that there are subcategory types beneath. You've got sections within a grade school, first, second, third, fourth grade, and you want to grab a certain random number of participants from that first, second, third, fourth grade group, or in more of a process improvement example, you've got certain product SKUs, and you want to grab a certain percentage or a certain random number of different product SKUs. You might do some cluster sampling. There's a great supplemental support video that walks through each of these through Elgin Community College and Professor Dan Kernler that I'll make a link to at the bottom of this video and I'll include in the optional videos section in which greater detail is given on each of these methods. So we've determined that sampling is needed. We have come up with ways to create random samples and used the appropriate sampling method that makes the most sense for the type of data that we're working with. The next big question that folks typically have is how much is enough? How big of a sample size should we use? And earlier in the program, we gave you some rules of thumb for sample size considerations, and it came down to the type of data that you were looking at. Did you have discrete data or continuous measurement data? Discrete countable data and continuous measurement data. And there were certain rules of thumb associated with each. If continuous, 30 or more data points. If discrete, 1,400 or more. But those are just general rules of thumb. Are there more elaborate ways to more sophisticated or rigorous ways to come up with your sample size, because maybe I can get by with a little bit smaller sample and it won't cost the organization as much, or maybe this rule of thumb isn't quite hitting the mark and I need to actually capture a little bit more to increase the level of confidence I have in that I understand what's really going on in current state, or that the future state data is a true reflection of what's going on in future state. Remember, in the end, samples are used to better understand what's going on either in current state or future state. So rules of thumb are nice, but let's take a look at a couple more rigorous ways. We'll look at sample size formula and sample size calculators next. So one of my favorite resources for sample size formula comes straight from the Minitab help content. So the online help associated with the statistical package Minitab came up with the drawings that I'm going to walk you through next. And I've never seen it laid out quite as simple and elegantly as these two drawings. So the first drawing that I want to show is how to calculate the minimum sample size. That's what MSS is for attribute or discrete data. And you'll notice in step one, we estimate the proportion of the process. And then in step two, we decide on the level of precision that we're looking for in the data analysis. And then we use this relatively straightforward formula to come up with the actual sample size, and walk through an example right here. And you can see both in the workbook and on screen that in this particular example, the minimum sample size that you want is a little bit greater than 1,400, our rule of thumb. They suggest a minimum sample size of 1,600 in this example. There is also the same step-by-step approach for continuous data, minimum sample size. Again, you estimate in step one what the standard deviation of the process is. Now, how you get this estimate, you could look to subject matter experts. If you've got data from, say, a different region that you think is a pretty close approximation, you might capture standard deviation from that, or you could use the standard deviation of your sample as an approximation for the standard deviation of your overall process performance. Another technique is to take a look at the historical data and grab the range and divide by 5. That will give you a quick estimate of standard deviation. If you remember, 6 standard deviations from the empirical rule cover 99.7% of the data. So this is a very basic approach for estimating standard deviation. Range divided by 5. You estimate standard deviation first in step 1. Then in step 2, you determine the precision that you require. And finally, in step 3, you enter the information into this pretty straightforward formula. And in this example, it walks you through, and you can see that if you walk through the example and plug in the data, the sample size is smaller than the minimum rule of thumb that we typically use for continuous of 30 or more data points. Nice way of coming up with minimum sample sizes for both continuous and discrete data types. Let's take a look at other formula that you can use for calculating your minimum sample size. In this next example, I'm pulling this straight from the workbook in the Lean Six Sigma Data Analysis program, and I've got the formula that is used to calculate the minimum sample size for proportional data or for discrete data, yes, no, pass, fail, in, out data. And the example is set up right here. Customer satisfaction survey has found that roughly the same proportion of satisfied and unsatisfied customers, so that's at 50%, 0.5. What's the sample size if we want accuracy to be plus or minus 3% of the true population at a 95% confidence level? And the answer, again, included in the workbook. Let me zoom in, and you just see how we plug those values in. And the minimum sample size here is less than that 1400 rule of thumb. Rules of thumb are nice, but for more precision, we would use the sample size formula. Let's take a look at a formula for continuous data next. In this next example, we're taking a look at minimum sample size calculations for interval scale data, a form of continuous data, and our sample formula is included here with a description of what each one of the variables are. And let me zoom in on the example itself. So you've got a survey study done on household incomes, shows that the average income is 40,000 and the standard deviation is estimated at 6,000. And we've talked earlier about how we estimate for standard deviation of the population, but we've got that estimate at 6,000. We'd like to know the survey sample size so that our margin of error is no more than $1,000 at the 95% confidence level. And the answer, again, right in the workbook, the answer is laid out in this manner. And you can see that for this interval scale data, the number is a little bit higher than our minimum rule of thumb for 30 or more data points if we wanted to be 95% confident with that interval data. There are sample size calculators that you can use as well. So right in Microsoft Excel's QI macros, there is a sample size calculator in the menu, and you can just plug in the values that you've got, and it will then spit out what the sample size will be. All of these sample size calculations assume that your samples are much, much smaller than the underlying population, or that the population data is much, much larger. Sometimes your population data isn't much, much greater, and in those situations, the formula that we just walked through would have to change. Are you sampling with or without replacement? Is the population much larger or not? Is there an equal likelihood that the different choices that could be chosen on, say, survey questions could all equally be chosen? On a scale of 1 to 5, are people likely to choose just as equally a 1, a 2, a 3, a 4, or a 5? That's not always the case, and then your sample size calculations are going to vary. In the end, remember, you're using samples to help you better understand what's going on in current state, and using samples to better understand the changes that have been made in future state if they've made an impact.